Richard James will continue these tutorials on ratios and variations with Ratios and Variations Tutorial 2. And of course we are continuing with problem number 9. In 1985, Angela and John decided to start a business. Angela invested, and that is what we have, that Angela invested right here. She invested $240,000, and John invested $160,000. And our duty is to determine John's share of the profit if the profit is shared according to the amount of money invested. Or we may say that the profit is also in proportion to the amount of money invested. And no doubt we have a ratio right there, the ratio of the money invested, and the profit will be according to that same ratio. The ratio of the profit is the same as the ratio of the amount invested. And let us write the amounts invested as a ratio, and we have it right there already. The figures will be less cumbersome if we reduce the ratio to its simplest terms. Divide each number in the ratio by 80,000. Well, we should see very quickly that 16 and 24 are multiples of 8. Or we may say, or take it a step further to say that we recognize that 8 is the highest common factor of 16 and 24. So we may go ahead and reduce by a common factor of 8. But notice that we have all of these trailing zeros here, and it is judicious and very simple to reduce the ratio if we eliminate those trailing zeros, taking them one at a time from each side, or eliminating the same number of trailing zeros that we have on this side and that we have on this side also. So we have 4 trailing zeros and we have 4 here. We may eliminate those altogether. So we will do that by dividing by 80,000. So if we divide by 80,000 on both sides, we'll have all of these being eliminated there, and we have the same thing here. And no doubt 8 into 16 is 2, 8 into 24 is 3. So that ratio is easily reduced, and we may do that in one single step. And of course we have subscripts here saying that this share belongs to Angela and this share belongs to John. As usual, we will add the numbers in the ratio in order to determine the number of units in which the entire sum is divided. Now, eventually, we are required to determine John's share of the profit. And John's share will be his share of the total profit. Therefore, if we have the ratio in which the profit is shared, it is judicious to find or to arrive at a number that represents the total profit, and that number will be the number that we will get when we add these two numbers that we have right here. And that is equal to 5. So the total amount is represented by 5 units. We may say that John's share of the profit will be the number of units that he gets divided by the total number of units. So we are saying that John gets a fraction of the total profit. And how do we determine that fraction? That fraction will be the number of units that John gets over the total number of units. That will be the fraction. And in order to determine his share, we will take that fraction and multiply by the total profit. So the John's share over the total number of units, that will be 2/5, and that we will multiply by the total profit. So that is the fraction of the total profit that John's share represents. Now we will go straight ahead and multiply by the total profit in order to arrive at John's share of the total profit. We will take the fraction that represents John's share that we have right there and multiply by the total profit in order to determine John's share of the profit. And from here on, the calculation is simple. Reduce by a common factor of 5. And there we have 5 into 15 is 3, but we cannot forget these trailing zeros. 3,000, and 5 into 5 is 1. Then we have 2 times 3,000. Multiply the numerators. 2 times 3,000, that will give 6,000, and multiply the denominators. 1 multiplied by 1 is equal to 1. So 6,000 divided by 1, and any number divided by 1 is equal to that same number. So the answer is $6,000. We may also take the approach in which we determine the size of each unit, and considering that John received 2 units, multiply the size of 1 unit by 2. So we are saying that because of the numbers that we have here in the ratio, the entire amount may be considered as having 3 plus 2 is equal to 5 units. So the entire amount may be considered to be 5 units. So the entire profit is equivalent to 5 units. And how did we arrive at those 5 units? We took the numbers in the ratio that we have here, 3 to 2. This one will get 3 shares, and this one will get 2 shares out of a total of 3 plus 2, out of a total of 5 units. So the total is represented by 5 units, and that total is actually $15,000. So we have 5 units are equivalent to $15,000. And we will go straight ahead, and that is what we said before, determine the size of 1 unit. We may find the size of 1 unit by dividing both sides by 5. So there we are, dividing both sides by 5, No doubt 5 divided by 5 is 1. So we will have 1 unit here. And 1 unit will be equivalent to whatever we will get when we divide this. And of course we know already it's going to be $3,000. So 1 unit is equivalent to $3,000. And we need to determine John's share. How many parts of the whole did John get? John got 2 parts. So in order to find John's share of the profit, we multiply the size of 1 unit, which is $3,000. That is the size of 1 unit by the number of units that John received. John received 2 parts out of 5, or 2 out of the entire amount. So 2 units are what John received. So 2 units multiply 2 by the size of 1 unit, and we know what is the size of 2 units. So 2 times 3,000 is equal to $6,000, and that represents John's share of the profit. Number 10. Jason wins $480 with a lottery scratch card. He decides to share his money between his friend Mary and himself in the ratio 5 to 7, and that's what we need to do first. How much money does each receive? That is what we need to determine first. Determine how much money each one receives. First, solve the problem by making use of the fact that the total number of units is 12, and that one of the individuals got 5 units out of 12, while the other got 7 units out of 12. Each fraction is then multiplied by the total. So we are thinking that we have first person getting 5 units and the other one gets 7 units. Therefore, we have a total of 12 units. Out of the total of 12 units, one individual gets 7. So 7 out of 12 of the total amount. So 7/12 of the total amount. And the other one gets 5/12 of the total amount. And all we need to do now is reduce by a common factor of 12. 12 into 48 is 4, but do not forget the 0, so 40, and 12 into 12 is 1 time. And we say 7 4s 28, and do not forget this trailing 0, so $280. And the other one we reduce again by a common factor of 12, and the same thing that we will get there. And 12 into this is 1 as usual, and we say 5 times 40 this time, and that will be $200. We may make use of the fact that the total amount of money, which is $480, is associated with 12 units. 5 plus 7 is equal to 12. One gets 5. The other gets 7. They have a total of 12 units. And these 12 units are equivalent to the total, because this 5 plus 12 represents the total amount of money. So these 12 units are representing the total amount. And what is the total amount? We have it there as $480. We may find the size of 1 unit by dividing both sides by 12. And 12 into 48 is 4. Well, we did that on the previous slide, no problem. So 1 unit is actually $40, and we will go straight ahead and make use of the fact that one individual gets 5 times the size of 1 unit, and the other gets 7 times the size of 1 unit. This one gets 5 units. This one gets 7 units. 5 times, what is the size of 1 unit? $40. So 5 times 40 is 200, and the other one gets 7 times the size of 1 unit. So $280. The problem goes a step further. Jason spends 20% of his share. What percentage of the $480 does Jason now have? Jason's share is about to be reduced by 20% because he spends 20%. So what do? Jason's share is the larger amount. He spends 20%. Therefore, he has 100 minus 20, which is 80% remaining, because the original amount of money that Jason has is 100% of itself. Therefore, by spending 20%, he will have 80% remaining. 100 minus 20 is equal to 80, so 80% remaining. Do not forget that when we see this written 80%, we are talking about a fraction whose denominator is 100, because we are saying that a percentage means out of 100. And if it is out of 100, it means that we are actually dividing by 100, or we may say that we have a fraction whose denominator is 100, because we are saying out of 100. A percentage is a fraction whose denominator is 100. Therefore, that 80 should be divided by 100. It may therefore be written as 80 divided by 100, which is the same as reduced by 2 places of decimal. So let us reduce by 2 places of decimal. There we are. The decimal point in a whole number is always considered to be at the extreme right. So reduce by 2 places of decimal. 1, 2. And what do? We may just throw in 0 right there, 0.80. And also we may eliminate that trailing 0 that we have right there, being insignificant. So it's actually 0.80, which is the same as 0.8. So whatever John has now, it is 0.8 times his share. That number may be used to multiply John's share, and being required to be written as a percentage of the original amount, we divide by the amount, which is that total amount of $480, and we will multiply by 100. And maybe that is a little bit more than a mouthful, so we will take it bit by bit. That number may be used to multiply John's share. remember that John's share is reduced by 20%. So it is now 0.8 of what it was before. So this is what it was before. Remember that John's share was the larger amount. This is what it was before. Now it is 0.8 of that amount. But whatever that new amount is, it is to be written as a percentage of the total amount of money that was shared. Therefore, that product is required to be divided by $480. And in our normal manner of finding the percentage, we multiply by 100. So, this is John's share of the profit. He's down to 80%, which is 0.8 of the original, so we multiply by 0.8. It is a percentage of the total profit to be placed over the total profit, therefore. And also, in the normal manner of finding a percentage, we multiply by 100, and it turns out to be 46.67%, or more accurately 46 2/3%. For problem number 11, we have that a party traveled to Europe for a holiday. The number of days they spent in France, as we have there, Spain and Italy, were divided in the ratio 3 to 4 to 5. They spent 9 days in France, which is the most important bit of information that we have right here. So they spent 9 days in France. But notice that we have these numbers in the ratio written with their respective subscripts in order that we are constantly reminded of which territory or country that each one of these numbers represent. So we have 3 for France, 4 for Spain, and 5 for Italy. And we have gone well ahead of time to say that the total number of units, that is 12. So the number of units that we have in total is 12. The number of days spent in France is 9. Those 9 days are associated with 3 units. So this is what we call the entering wedge. Right. The fact that 9 days are associated with 3 units. So we have 3 units and we have right there 9 days. Therefore, half our work has already been completed, because all we need to do is, as usual, find the size of 1 unit by dividing both sides by 3. And when we have done that, 3 into 3 is 1, so we have 1 unit, and 9 over 3 is equal to 3. So 9 divided by 3 is 3, so 1 unit is actually representing 3 days. The total number of days is 12. As a matter of fact, according to the statement of the problem, we need to find the total number of days. So the total number of days is 12. Also, we also need the number of days spent in Italy. So those are the 2 things that we need to determine according to the statement of the problem. 1, we need to determine, as we have right there, how many days was the complete holiday. And then, how many days did they spend in Italy? How many days for the complete holiday, and how many days spent in Italy? the total number of days is 12 times the number of days in 1 unit. And the number of days spent in Italy is 5 times the number of days in 1 unit. So we have 1 unit is representing 3 days, and we need to know the number of days in the entire holiday. We also need to determine the number of days spent in Italy. Well, for the entire holiday, we have a total of 12 units, which is the sum of these numbers, the numbers that are in the ratio. So the total number of days is 12 times the number of days in 1 unit, and the number of days spent in Italy is 5 times the number of days in 1 unit. So we have 12 times 3, 12 units, and each one is 3 days. So 36 days for the entire trip, and 5 units for Italy, as we have right here. So 5 times the number of 1 unit. 1 unit is 3 days. 5 threes, 15 days. We may also find a factor of association that relates the number of days spent in France to its number in the ratio, because we know that we have for France 3 units, and we remember that that represents 9 days. So what is the factor of association? How is 9 related to 3? Clearly, 9 is equal to 3 times 3. Therefore, all of those numbers in the ratio and the total also are related to their respective days spent in the same way. So we have 3 related to the number of days by multiplying by 3. Therefore, 4 will be related to the number of days spent in Spain by multiplying by 3. And the same for Italy, related to the number of days spent in Italy by multiplying 5 by 3. The same is true for 12, because in all we have 12 units. The factor of association is 3. Therefore, we will take 12 and multiply by 3, and no doubt we can reflect on what we did on the previous slide and realize that we are not too far from it, because the factor of association is 3 and the size of 1 unit is 3. Therefore, to find the number of days spent in Italy, we multiply its number by the factor of association, and that total number of days may be found by multiplying the factor of association by the total number of units. So we said before, how do we move from 3 to 9? 9 is equal to 3 times 3. So how do we move from 4 to the number of days? 4 times 3. How do we move from 5 to the number of days? 5 times 3. Now, we do not do any different for the total number of days. The total number of days is associated with 12 units. Therefore, we will say the factor of association is 3. 12 times 3. So we have 5 times 3 for Italy is equal to 15 days, and 12 times 3 for the entire trip is equal to 36 days. Also, notice that the factor of association is equal to the number of days in 1 unit from the previous solution. So if we run all the way back to the original solution, we'll realize that 1 unit is equivalent to 3 days, and we are saying on this slide that the factor of association is also 3, and we are using it right here, so there is no harm done. it does not matter what we call it. The factor of association or the size of one unit, they will be the same, they will have the same effect, and no doubt they will accurately solve the problem. For a scale that is given that represents a comparison between a diagram on a map and an actual piece of land that it represents, the first number, that is usually 1, represents the length on the map. The other figure that is not equal to 1 represents the actual length of the piece of land. So there we have a scale for a map. The large number for the map or for the scale, that large number represents the actual length, and this one, which is usually equal to 1, represents the distance on the map. So this one represents the actual distance, and this one represents the distance on the map. Usually the figure on the actual side is larger. It is usually larger, but it is not impossible to have a scale written in the reverse order, as we shall see by the time we are through with this tutorial. So usually the figure on the actual side is larger. Therefore, for any conversion between a distance on a map and the corresponding distance in actuality, the actual distance should be larger. We need to understand this in the context that in the ratio, the two numbers are in the same unit. So for the scale of a map, these two numbers are in the same unit. So if this is in centimeters, when you multiply by this, your answer is still in centimeters. And if this is in centimeters, you may want to divide, or maybe you say that it is in kilometer. You may want to convert to centimeters first. But if you do not do any conversion between units, if this is in kilometers and you use this scale, then your answer will be in kilometers. Well, if it is an awkward figure, well, it should be in the end an awkward figure, then you can convert to centimeters, so it will make a lot more sense on the map. But as long as you are using this scale and this scale only, while you are using the scale for the map, there is no change in units. So let us read this again. Usually the figure on the actual side is larger, and when we say the actual side, we mean this number. So usually the figure on the actual side is larger. Therefore, for any conversion between a distance on a map and the corresponding distance in actuality, the actual distance should be larger. We need to understand this in the context that in the ratio, the two numbers are in the same unit. The one on this side is larger. Well, if you draw a map to a particular scale, if you're drawing the map of a city, then what you have on your diagram is expected to be smaller than the actual length in the city. Or you may say what you have for an actual length in the city should be larger than what you have being represented by that actual distance on the map. So what you use on the map to represent that actual distance, the representative on the map, should be a smaller figure. After making calculations using the scale, then we may go ahead and make conversions as necessary. Some of the most common conversions are to make use of 100 centimeters is equal to 1 meter, 1,000 meters is equal to 1 kilometer, and 100,000 centimeters is equal to 1 kilometer. This one, be careful of it, and also this one. We may have others, meaning we may have other equations of conversion between units, but we will use them as necessary. At this stage, conversion factors should not be beyond us because we know them from primary school, and those that we do not know, we know how to derive them. So we do not have to worry too much about these conversion equations because we know some of them, and the ones that we did not remember, we have them right here. And for the ones that we need to use that are not mentioned there, we know how to derive them. One other thing that we need to bear in mind is that as it pertains to area, we need to use the square of the scale factor. So let us take a look at the reason for this. So if we are converting between area on a map and area in actuality, then we need to consider the square of the scale factor, and we will take a look at the reason for this. Look at the squares that we have there. Although they are not drawn to scale, well, it should not be drawn to scale because this one does not look actually square. So although they are not drawn to scale, it is clear that the length of one side of the second is 5 times the length of each side of the first. So we need to be aware of the fact that one side of the second is 5 times one side of the first, because this one is 1 meter, this one is 5 meters. This one is actually 5 times this. No problem with that. The ratio of their sides is therefore 1 to 5. So the ratio of the sides of this square being 1 meter and this one is 5 meters, 1 to 5. Calculate their areas. The first area, the area of a square or any rectangle, may be found by saying length times width. But for a square, the length and the width are the same. So we have 1 multiplied by 1, and that is equal to 1 centimeter squared. And the other one, we have 5 multiplied by 5, which is equal to 25 centimeters squared. Of course, in finding the area of a square, we just square one side. Or we may make use of the fact that a square is a rectangle whose length and width are the same. So multiply by 1, multiply by 1. So 5 times 5 and 1 times 1. So their areas are in the ratio 1 to 25. What is the area of this one? The area of this one is 1 centimeter squared, and the area of this one is 25 centimeters squared. So we have 1 to 25. So their areas are in the ratio 1 to 25. Surely 25 is equal to 5 squared. Therefore, in converting between areas, we need to square the scale factor. Look at this scale factor, 1 to 5, and this one is 1 to 25. So square 1, we get 1. square 5, we get 25. Therefore, when we are converting between areas on a map, we need to square the scale factor. Generally, in order to find the scale factor between areas, we need to square the scale factor between lengths. So if we need to find the scale factor between areas, we need to square the scale factor between lengths, and that is general. The distance between M and N on the map is 4.4 centimeters. Remember that 1 is usually associated with the map, which is given as 4.4 centimeters. Write that down. Right. So what we have here is this side, the 1 is associated generally with the map, and the distance on the map is 4.4 centimeters. And this is our scale of enlargement or scale of reduction, depending on which direction we are looking at it from. So let's go. The actual distance is on this side of the larger number. So here we have 1 and we have 250,000. Well, no problem seeing that 250,000 is actually the larger of these two numbers. So we have on the map 4.4. And what do we imagine that we will get here? Well, if we are moving from the map to the actual, the number that we are about to get here has to be larger. So we have 1, which is a small number, and 250,000, which is a large number. So when we do the calculation to the actual figure has to be larger. So how do we arrive at that actual figure? So the actual distance is on this side of the larger number. Therefore, in order to obtain that larger number, we will multiply by the factor of 250,000. And what do we get? We get 1,100,000. And of course, this could have been done mentally. Do not forget that when you are multiplying by this number 25, that 25 is related to this number that we have here, 4. And do not forget that 0.25 is a quarter. So if 0.25 is a quarter, it is as if we are taking a quarter of 4. A quarter of 4 is 1, and a quarter of 4 is 1. So only the discrepancy with the zeros that we need to iron out. The rest of the calculation is just straightforward. So this could have been done mentally. Now what do we need to be reminded of? Remember that the conversion is done in the same unit. We need to convert from centimeter to kilometer in the end. On the next slide, we will make use of a conversion equation between centimeters and kilometers. So when we have done this calculation, which is multiply this by 250,000, this 4.4 was given to us in centimeters. This is actually in centimeters also, because the scale, or making a calculation in the scale, does not change the units. So this is in centimeters. So let us use an equation on the next slide to convert to kilometers on the map, as required by the statement of the problem that says that calculate in kilometers the actual distance of n from M. So calculate in kilometers. So what we have done here, use the conversion factor, no change in units. So this is 1.1 million centimeters. and we need to convert that to kilometers. Do not forget that 100,000 centimeters is equal to 1 kilometer. Therefore, in converting from centimeters to kilometer, the number that you get will be smaller. Notice that the number on the centimeter side is larger than the number on the kilometer side. So in converting from centimeters to kilometers, the answer should be smaller. The length of the map was given in centimeters. Therefore, the number obtained from the conversion process is also in centimeters, which is that one. And what do we do with it? Notice that in the equation that we have for the conversion between centimeter and kilometer, the larger figure is on the centimeter side. As I said before, the larger number there. Or, if we prefer, we may say that the smaller number is on the kilometer side. Therefore, in converting from centimeter to kilometer, the number will have to be made smaller. We will achieve that by dividing by 100,000, which is the number that we have in the conversion factor. So we are going to the smaller, not smaller unit, because a kilometer is 100,000 times a centimeter. But the number that accompanies the unit is smaller. So when we divide that 1,100,000 by 100,000, we get 11, and that's 11 kilometers. Number 13, a scale that we have right there, 1 in 15,000, is used to draw the map of a city. Calculate the actual distance in kilometers between 2 points in the city which lie 87 centimeters apart on the map. So, the actual is what we are attempting to find, but we have the distance on the map as 87 centimeters. Do not forget that 1 in the scale, which is this one, is associated with the distance on the map that is given as 87 centimeters. The actual distance is on the side of the larger number. Notice, side of the larger number. Therefore, in order to obtain the larger number, we will multiply the distance on the map by 15,000. But how do we know that we are actually converting to a larger? Because 1 is associated with the map, 15,000 is the actual, or representing the actual. Therefore, if we need to find the actual, we need to multiply that by, which this 87, by 15,000. And what do we have there? 1,305,000. That is our answer. And that answer is in what? Is it in kilometers, centimeters, or meters? We were given 87 centimeters to convert with the scale of the map. In converting in the scale of the map, there is no change in unit. Therefore, this is representing the actual distance in centimeters. Conversion is done in the same unit. Therefore, the answer is 1,305,000 centimeters. The statement of the problem requires that the actual distance be converted to kilometers. On the next slide, we will make that conversion. We know that 100,000 centimeters is equal to 1 kilometer, as we used in the previous problem. And the length of the map was given in centimeters. Therefore, the number obtained from the conversion process is also in centimeters. That is also in centimeters. There is no change in units when we are using the scale of the map. Therefore, if we are just using the scale of the map and nothing else, if we started with centimeters, 87 centimeters, when we do our calculation, we will get our answer also in centimeters. Notice that the equation that we have for the conversion between centimeter and kilometer, the larger figure is on the centimeter side, or if we prefer, we may say that the smaller number is on the kilometer side. Therefore, in converting from centimeter to kilometer, the number will have to be smaller. We will achieve that by dividing by 100,000, which is the number that we have here in the conversion equation. And as I said before, the number being smaller does not mean that this one is smaller. Because actually 100,000 centimeters are in 1 kilometer. So there we are, just dividing by 100,000, and we should get 13.05 kilometers. No harm with that one. Is there anything else to write home about? Sure there is. The field is actually 225 meters long. Which field is actually that 225 meters long? It is said that the actual length of the playground in the city is 225 meters. Calculate in centimeters the length on the map. So the field is actually 225 meters long. 225 meters long. There is where we will have it. The actual is 225 meters. And we need to make our conversion. 1 meter is equal to 100 centimeters. In converting from meter to centimeter, the number will therefore be bigger. We need to multiply by 100. But why are we doing that now? We have not used the scale of the map as yet. Why are we going straight ahead to multiply by 100 first? Maybe we will discuss that in the tutorial. Maybe not for this problem, but for sure we will take a look at the reason for doing this. So the conversion between a meter and centimeters is 1 meter is equal to 100 centimeters. We need to convert this given in meters to centimeters. So the larger number is on the centimeter side. Therefore, in converting to centimeters, we have to have a larger figure than what we have here. We need to multiply by 100. And we have 22,500 centimeters. Now, we need to convert that actual length that is given in centimeters to the corresponding length on the map that is given in centimeters. Also, in the scale, the smaller figure is associated with the map. In order to get that smaller figure, we need to divide by 15,000. So this is what we have in centimeters. Has to be in centimeters because we just made a conversion from meters to centimeters. And when we make the conversion using the scale of the map, with this figure to do our conversion, we will arrive at our answer that will be in centimeters also. Therefore, if we are solving a problem like this, we may convert between units before we use the scale of the map, or convert between units after we use the scale of the map. But there is no change in units when we are applying the scale of the map only. So we are going to the distance on the map. This 15,000 is a larger number than this one that we have here. So if we are going to the number or the corresponding length on the map, we will definitely get a smaller figure. Therefore, we will take this 22,500. In order to get a smaller figure, we will divide by this 15,000. So divide that by 15,000, and what do we get? 1.5 centimeters. Of course, 1.5 should not be so shocking, because we know that 225 is related to 15. As a matter of fact, 225 is the square of 15. So if we divide 225 by 15, we should get 15. The only thing that we need to iron out in the end is these trailing zeros and how that will affect the position of the decimal point. And I'm sure that that is not difficult either, because these two will go with these two, and there's another one here, so we'll have one place of decimal. So that's pretty straightforward. Now we are gone into area, and as we get here, one might be thinking, right now is where we need to apply the square of the scale factor. But let us see. Given that the area of the playground on the map is 1.8 centimeters squared, calculate the width of the playground as shown on the map. So all we need to do is calculate the width as shown on the map, and very doubtful that we will have to apply the square, because we are told that the playing field has an area of 1.8 centimeters squared on the map, and we need to find its width. That's what we need to find. But we have found something else. So we have found the length to be 1.5 centimeters, and we know that the area of a rectangle is given as area is equal to length times width. See, do not forget that the length that we have there was already calculated, and the area of a rectangle is given by area is equal to length times width. We have the length and we have the area. So area is 1.8 centimeters squared, and the length is 1.5 centimeters. So substitute those into the equation. So for area we have 1.8, for length we have 1.5. Throw those in, and what do we know? We have only one equation. Well, we had one equation to begin with, but additionally we now have only one unknown. Therefore, we may very quickly find that one unknown, which is what we are always able to do if we have a single equation with a single unknown. So find W by dividing the equation by 1.5. Then finish up by writing W on the left hand side. So here we have W being multiplied by 1.5. In order to eliminate this 1.5, we will divide by 1.5. So divide that by 1.5. But this is an equation. Whatever we do to one side, we also need to do it to the other side. So divide both sides by 1.5. And can anybody tell me what is 1.8 divided by 1.5? 18 is 1.5 times what number? Because 1.5 is 1.5. And we are not saying 1.8, we are saying 18. So we will have to make that adjustment in the end. 18 is 1.5 times what number? Well, try 12. Half of 12 is 6. And 1 times 12 is 12. So 1 times 12 is 12. And a half of 12 is 6. 6 plus 12 is 18. Therefore, 18 is actually 1.5 times 12. So we know that what we will have on this left hand side is actually 1.2 centimeters. And turn the beat around, and we have W is equal to 1.2 centimeters. Very nice. Let us attempt to take a broader look on the solution of our previous problem. Here we have the scale that is used to draw the map. Where is that scale? So we will take a broader look on the solution of our previous problem. And there we have the scale that is used to draw the map. As we discussed before, the 1 is usually in reference to the measurements on the map. So 1 is associated with the map. And we are saying that in a graphic way by showing you actually that 1 is associated with the measurements on the map. Also, as long as we are using that scale to convert, we are assuming that the units are the same. That scale is only a scale of enlargement if we are converting from a length on the map to an actual length, or may be used for reduction if we are converting from an actual length to its corresponding length on the map. So this scale only acts in a way if we are converting from the map to actual as a scale of enlargement, and we may use it for reduction purpose if we are going from an actual length to a length on the map. That is its only use. It has nothing to do with conversion between units. Let us again convert the 1.4 centimeters on the map to its corresponding distance in kilometers in actuality. So go straight ahead and do that. In a regular scale conversion, that is, one that does not involve a conversion in units, the figure on the actual side is always larger than the one on the map. What will we therefore use that 250,000 to do with that 4.4 centimeters? Surely we will have to multiply, because we have this 4.4 centimeters on the map, and we are making a conversion to actuality, and we have that the figure on the side of the map is 1, and the figure here is 250,000, which is the larger figure. Therefore, if we are converting in this direction, the figure that we will end up with has to be larger. So what will we take this 4.4 centimeters and do with this 250,000? We will have to multiply, and there we have our 1,150,000. 100,000. Notice that the answer is also in centimeters, which is the same unit that we started with. That is how it has to be. The scale of the map does not affect the units. Therefore, when we have a problem that involves a change in units, as this one, it is best to convert between units before or after we use the scale of the map. Later on, we will show that we may combine the two steps and perform them in one. The steps are 1. Use the scale of the map, and 2. Convert between units. So those are the two steps that we will demonstrate how we may do them in one. We will convert by making use of the scale of the map, and we will convert between units, and we will demonstrate how those two steps may be done in one. But we are saying that when we are converting using the scale of the map alone, there is no change in units. There is a conversion equation. The blind can see that it may be used to convert between centimeters and kilometers, because of course we have 100,000 centimeters is equal to 1 kilometer. Therefore, we do not have to ask what are the units between which we will convert, or we will make a transfer when we are actually about to use this equation. It is not that a centimeter is larger than a kilometer, because we know that it takes 100,000 centimeters to make a kilometer. But take note that the larger number is accompanying the centimeters. So notice that the larger number is accompanying centimeters. That means if we are converting from centimeters to kilometer, the larger number is on the centimeter side. So when we go to kilometers, the number will be smaller. And if we are converting from kilometers to centimeters, the larger number is on this side. Therefore, after we have done the conversion, the number has to be larger than the original. Conversely, the smaller number is accompanying the kilometers. Therefore, for any conversion from centimeter to kilometer means that we are going from the side of larger number to the side of smaller number. The conversion may be completed by dividing by 100,000. That will cause the number representing the length in kilometer to be smaller than the number representing the length in centimeter. This is consistent with how the scale is written. So we have 1.1 million, or we may say 1,100,000, and we are dividing that by 100,000, and we are arriving at 11 kilometers. Because of how this is written, we are moving from centimeters, which is all of this, to kilometers, and the number gets smaller. Well, it is represented by a smaller number if we accompany it by this unit. Some candidates may demonstrate great familiarity with the conversion that involves the scale of the map, and also one that converts between the units, and may complete the two steps of the problem in one. So there we have 4.4. They may do the two steps in one by saying the scale of the map may be used to increase the length of 4.4 centimeters on the map to the actual length. So let us use it to increase by multiplying by 250,000, which is what we have for the scale of the map. Understanding that the conversion does not involve a change in unit, a further conversion has to be done in converting the actual length in centimeter to kilometer. We will therefore make use of that other scale. So we are converting this now that we have in centimeters, we are converting it to kilometers. Going from centimeters to kilometer, the figure on the centimeter side is larger, so we are going smaller. We need to divide by 100,000 as we have right there. And what does the answer turn out to be? Just as we had before. So we could have done that in one step. Use the conversions factor of the map, multiply by 250,000 to get the actual. But the actual is in centimeters, and we need to convert that to kilometers. We divide by 100,000. Let us use our scale to convert an actual distance that is given in kilometer to a corresponding length on the map. So give something in kilometers and see. Right. So give that 22.5 kilometers. We are attempting to use our scale to convert an actual distance that is given in kilometer to a corresponding length on the map. And the corresponding length on the map will be in centimeters. The actual distance is 22.5 kilometers on the map, and we will convert that to centimeters. The actual distance is 22.5 kilometers, and we will convert that to centimeters on the map. We have three options. What are the three options? 1. Convert the kilometer to centimeter first, then use the scale factor to convert to the map. What does that mean? That means we have the choice of converting this to centimeters, because we will eventually have to get there, because we will be converting to centimeters on the map. So we have a choice of converting this to centimeters first, then use the scale of the map to convert the actual to the length on the map. So convert to centimeters and then tell what that will be on the map. The other option is convert to the map. So say what the distance will be on the map, but that will be in kilometers, and then we need to convert the kilometers to centimeters. Or 3, do both conversions in one, as we have demonstrated before. Irrespective of the method used, 1 or 2, we will still take a go at 3. The problem is which of 1 or 2 do we use? Which one do we use? And if that is a question that is to be answered logically, then we must, or we should, have some logical reason for whatever answer we supply. Let us do a simple analysis. Let us imagine using 2 first, which is convert to the map first, and then convert that kilometer to centimeters. So let us do a simple analysis. Let us imagine using 2 first. If we are converting from actual to the map, according to what we have there in the scale, the larger number is on the actual side. So from actual to map, the larger figure is on the actual side. Conversely, the smaller number is on the map side. Therefore, the conversion will require that we go from a large number to a small number, from the large actual to just 1, from the large actual to a smaller. So the conversion, if we are going to do that conversion first, requires that we go from large to small. So if that is the case, what will happen? That will require that we divide 22.5 by 250,000 first or immediately. So 22.5 divided by 250,000 will give a very small number. As a matter of fact, the result will turn out to be a very small decimal fraction. It is not that the decimal will not work, but in mathematics, the better alternative is always to use whole numbers if possible. Do not include an unnecessary fraction. That is one of our do not include rule. So do not include an unnecessary fraction. We will actually show that the horrible decimal is in no way less efficient at yielding the correct answer than its whole number counterpart. So we are taking a look at the option of converting from actual to the mapped first. And what do we know? That if we do that, we stand the chance of ending up with a very small decimal fraction, which, as we said before, will not cause the answer to be different or wrong, or cause it to be less efficiently arrived at. It is only that we are saying that if we do not have to include fractions, then we do not do it. But that does not make it any worse than the other one. So it is a matter of just choice, choosing not to use the fraction if we have a choice. And as a matter of fact, we do. Let us do one first. Convert from kilometer to centimeter first. So let us do that first. So convert from kilometer to centimeter. Do you remember what we had? We had 22.5 kilometers. And we need to convert that to centimeters first before subjecting that to the scale of the map. Notice that the figure on the centimeter side is larger. Therefore, in the conversion from kilometer to centimeter, the number will result in a larger number. Larger means that we need to multiply by that factor of 100,000. The result that we obtain must be consistent with the numbers in the conversion equation. For any pair of corresponding lengths, the larger figure must always be on the centimeter side, and the smaller figure must always be on the kilometer side. So if we are using this conversion factor, if we are going from kilometer to centimeter, then the number that we get on this side should be larger, being consistent with what we have right here. So let's go straight ahead. We are going from kilometer to centimeter. Therefore, to get that larger number being consistent with this equation, the larger on the left hand side, the larger for centimeters, then we need to multiply by 100,000 and we get 2,250,000 centimeters. After that, we will subject the number that we have right here to the scale of the map. This is still the actual length because we have not subjected it to the scale of the map. So what we have here, though it is in centimeters, is not the distance on the map, or this would be far-fetched to be the distance on the map. The distance on the map, we do not imagine could be 2 million centimeters plus. So this is the actual distance, and that we will convert. Let us put that on the actual side because it's actually the actual distance. Notice that in the scale of the map, the figure on the actual side is larger than the figure on the map side. Conversely, the figure on the map side is smaller than the figure on the actual side. Therefore, going from actual to the map will result in a smaller figure. We will obtain that smaller figure by dividing by 250,000. So what do we say? Large number here, large number here. We need to go onto the map, so we will get a smaller figure. We need to divide by this scale factor of 250,000. And can anyone tell me what this will turn out to be? Because we are saying we can make some calculations in our minds. Well, we can look at this in two ways. We can look at this as, do not forget that 25 is related to 4. So we need to multiply this by 4 if we are dividing by 25. Well, we know it's not actually 25 because of these zeros, and this is not actually 225. But laying that aside, let us treat it in that way, because as a matter of fact, all of these, we have 1, 2, 3, 4 zeros here, and we have 1, 2, 3, 4 zeros here. So we may go straight ahead, eliminate these, and say 25 is related to 4, dividing by 25 is multiplying by 4. So this is 2 and a quarter, 2.25. So if this is 2.25, which is 2 and a quarter, double 2 and a quarter, we get 4 and a half. So we need to multiply by another 2. 4 and a half times 2 is 9. So that is our answer. That is one way to look at it. So 9 centimeters. Is there any other way to look at it? Well, there's another way. We have 225, which is the square of 15. If we square 15, 3 5s 15. We square 3 and we square 5. So the square of 15 is square 3 and square 5. This one is the square of 5. 25 is square of 5. So if we take out the square of 5, what will be left is the square of 3, which is 9. That is the distance on the map that corresponds with 22.5 kilometers in actual distance. As shown before, the entire conversion may be completed in one step by taking the 22.5 kilometers, and what do we do first? Let us demonstrate this by first considering that we will first convert kilometers to centimeters as before. So convert kilometers to centimeters. Remember that a larger number is on the centimeter side, so we multiply. Right. We will then use the scale of the map to convert from actual length to map length. This will be a reduction because we are going from actual to the map. So we need to go down. We need to get a smaller figure on the map. Therefore, we will divide by the scale of the map, which is 250,000. Right. And that will give us 9 centimeters. Let us rewrite the fraction that we used to determine the answer. Convert an actual distance given in kilometer to distance on the map in centimeters. So let us rewrite the fraction that we used to do that. That is the one that we used to do that, which is the one that we have right there. Let us also rewrite the other fraction that was used to convert a distance on the map to actual distance. Now, before we do that, take a look at what we have right here. What we have done is single out the number that we had before, and notice that we are multiplying by 100,000 and also dividing by 250,000. What we do here is just write this one over this one as a fraction and cause that to be the fraction of conversion, because what we are converting is actually this. So we may separate this one from the fraction. So this is a fraction of conversion. And let us also rewrite the other fraction that was used to convert a distance on the map to actual distance, which is that one. The one that we used before. We are just rewriting that. Notice that the fraction that we use to convert centimeter on the map to actual distance in kilometers is the reciprocal of the fraction that we use to convert from actual distance in kilometer to distance on the map. How useful is this observation? So this one was used to convert from actual distance in kilometer to map distance in centimeters, and this one was used to convert from map distance in centimeters to actual distance in kilometers. How useful is this observation? Sometimes we have a problem in an exam that requires us to convert centimeters on the map to actual distance in kilometers. We put our brain through some high concentration exercise in order to ensure that we get it right. The next part of the problem requires that maybe we have the problem in the exam and then we are given this first and then we are given the other one. The next part of the problem requires that we convert from actual distance in kilometer to distance on the map in centimeters, which is the opposite of what we had before. We therefore do not go through the same hell that we have for the previous section. All we need to do is the reverse of the process if we have taken 2 steps in arriving at the answer, as we have done numerous times, or do the reciprocal of the fraction if we did it in 1 step. So whereas one part of the problem is requiring centimeter on map to kilometer in actuality, the other one is going kilometer in actuality to centimeters on the map. Therefore, if we find one by a particular process, all we need to do is reverse the process. But the reversal of the process may be as simple as finding the reciprocal of a fraction. Therefore, we do not have to go through the same mental duress that we would have gone through in doing the first part, going through that same high level concentration in order to do the second part. All we need to do is realize that the processes are opposite and just do the opposite thing. Let us demonstrate that we can convert in the scale first, irrespective of the fact that we will get that repulsive fraction. So let us demonstrate that we can actually convert in the scale first, although we will get this repulsive fraction. The 22.5 kilometers is an actual distance. It therefore belongs on this side of the larger number. If we will convert it to the distance on the map, we will be reducing by that scale factor. We will therefore have to divide by 250 250,000. So do that. Divide by 250,000. So 22.5 divided by 250,000 gives 0.00009 kilometers. So that is what our answer will be if we would have chosen to convert using the scale of the map first. Because as a matter of fact, we can do anyone that we please, as we are demonstrating here, that anyone that we choose, we will get or will arrive at the same answer. So let us go straight ahead and divide by that 250,000, and we get that fraction that we were running away from. Notice that the distance stays in kilometers because we are using the scale of the map to convert. There is no change in units when we are converting by making use of the scale of the map. So there is no change in units when we are converting in the scale of the map. Therefore, we have this in kilometers. This will also be in kilometers because we are just using the scale of the map. And when we just use the scale of the map, we do not have a change in units. The distance that we have there, although it is in kilometers, it is the distance on the map that an actual distance of 22.5 kilometers represents. So although it is in kilometers, it is what the actual distance corresponds to on the map. So this is actually a distance on the map, although it is given in kilometers. And we should not be amazed that if kilometers or a distance in kilometers is given on a map, that it will be a very minute fraction. So it is a very minute fraction, and that is what we expect if we are about to write the distance on a map in kilometers. There is our conversion equation converting centimeters to kilometer. So we have finished with the conversion of the map. So we are just converting units now. So that is our conversion equation. Use that equation to convert from kilometer to centimeter. According to that conversion equation, the larger figure is on the centimeter side. We will therefore convert from kilometer to centimeter by doing what it takes to arrive at that larger number. We will therefore multiply by 100,000. So we are converting from the smaller number kilometer to the, well, the unit kilometer is not smaller than the unit centimeter, as a matter of fact, but the accompanying number is smaller to the accompanying number, which is larger here. Therefore, if we are converting from kilometers to centimeters, the accompanying number has to be larger. Therefore, whatever we get right here, we need to multiply by 100,000, and that will give 9. And remember how we do that in primary school? Because this has 1, 2, 3, 4, 5 zeros. We will increase this by 5 places of decimal. 1, 2, 3, 4, 5. Therefore, the answer turns out to be the same and also correct, irrespective of the approach that was taken, as long as it is mathematically sound. It is for us to understand that it is possible for a scale that is used in drawing a diagram to have the smaller number in the actual side. For example, in science, we are always drawing diagrams of cells and some other microscopic particles. Surely, in these cases, the size on the diagram will be very much larger than the actual size. So that when we are doing scientific diagrams, not all of them, because I'm sure that the scale that we use there, which is for a map, in that particular case is also a scientific diagram. But in terms of maybe the diagram of a cell, if we draw the diagram of a cell, surely that diagram is going to be larger than the actual size. So it is for us to understand that it is possible for the scale that is used in drawing a diagram to have a smaller number in the actual size. For example, in science, we are always drawing diagrams of cells and some other microscopic particles. Surely, in these cases, the size on the diagram will be very much larger than the actual size. There we have it. So we cannot switch it around, the same numbers we are using. So it is possible that the one on the diagram is very much larger than the actual, and that we will expect if we are drawing the diagram of a plant or animal cell or a blood cell. Therefore, even at this early stage, students should not be thinking that a scale can only be written in one way. In attempting to make the adjustment, one does not need to be confused. In this particular case, the number on the diagram side is larger. Therefore, while making the conversion to a particular length on the diagram, the number will be larger than the one in actuality. Also, keep it in your mind that during a scale conversion, there is no change in unit. So, we can make the adjustment. We do not imagine that we can be overtaken if something turns out to be a little bit different from what we would have expected by the examples that we have gone through. It is not the example, but is the principle that those examples are enforcing. And if we have a very good grasp of the principles, irrespective of how information is given to us, we will have the correct interpretation of the information, and we will do what is correct with that information. There is no change in unit because it is always understood that for a scale, the lengths on either side are in the same unit. As a matter of fact, that is one reason for the numbers in a scale not being accompanied by any unit. We will take a closer look at this on the next slide. So there is no change in units because it is always understood that for a scale, the lengths on either side are in the same unit. That is why there is no change in units, because it is understood that the lengths are in the same unit. As a matter of fact, that is one reason for the numbers in a scale not being accompanied by any unit. We will take a look on the next slide why this is so. The numbers in a scale are assumed to be in the same unit, and this is why there is no change of unit when a scale is used to convert a diagram to actuality. Let us write the scale with the numbers having the same unit. So those have the same unit, and that is a scale that represents conversion, maybe in length, from one diagram to an actual length. Ratios generally have their most efficient use if they are written in their simplest terms. let us write the ratio in its simplest terms. This we will do by first reducing it by a common factor of 5. So reduce that ratio by a common factor of 5. 5 into 10 centimeters, 2 centimeters. 5 into 5 centimeters, 1 centimeter. The units are the same and may also be treated as a common factor. We may therefore have a further reduction of the fraction by a common factor of the units because they are the same. So they are common factors. So 2 centimeters to 2 and 1 centimeter to 1, eliminating those centimeters. With the units cancelling, there is no unit in the scale. So the units are eliminated because they are the same. We are reducing the ratio to its simplest terms. And if we are doing that, everything that is called common factor will have to go. And the units are common factor and they are gone. We may therefore arrive at the question, why is a scale for a map written with the intention to have the numbers having the same unit? So why is the scale of a map written with the intention to have the numbers having the same units? This is for convenience and also an exercise of simple common sense. Scales may be written in different units and the calculations using them may prove to be straightforward. However, making use of the same units facilitates the reduction of the ratio to its simplest form. Remember of old that the best way to reduce a ratio to its simplest terms is to ensure that the numbers in the ratio are in the same unit. So, scales may be written in different units and the calculations using them may prove to be straightforward. So it is not impossible to write a scale using different units and the calculations using them can turn out to still be straightforward. Maybe we will look at that scenario in a subsequent tutorial. However, making use of the same units facilitates the reduction of the ratio to its simplest form. And remember also that the best way to reduce a ratio to its simplest terms is to ensure that the numbers in the ratio are in the same unit. Remember that a ratio may be written as a fraction. Maybe in the reduction of a fraction, it is quite or more obvious that the units will eliminate each other. So we are saying that that is a large ratio that we have there on the screen. And what do we do? Since for some it might not be plain that we can actually eliminate the units, then we may say that we may write this ratio as a fraction, and after we have done that, we reduce the fraction. It is more obvious that the units will eliminate each other. Right, so the centimeters are gone because we are just reducing those fractions by those common factors. Anything that we see there as common factor, they will have to go. Now, reduce by a common factor of 5. 5 into 10 is 2. 5 into 5 is 1. And that is all there is to it. Not leaving any stone unturned, I attempted to go one step further in demonstrating the reason for the numbers in the scale of a map not having any unit, and as a consequence, there is no change in units when the scale is applied. And we have said that 1,000 times, that there is no change in units when the scale is applied. And we have attempted in the last slide or two to to show why there is no unit in the numbers that are used in the scale, and as a consequence there is no change in units. The additional step is the use of fraction reduction. If there was any doubt that the units would have been eliminated provided that they are the same, I hope that that doubt is dispelled by observing the reduction of the fraction, if it was not dispelled by the reduction of the ratio to its simplest terms. So we have gone one step further to show that the numbers having the same units will cause the units in the ratio to be eliminated. And if it is not so plain using the ratios alone, then I have taken a bit further to go to fractions, and also to show that the fraction will actually reduce to numbers that do not have any units because the units are eliminated.